receiving.
I've got to show you that.
Yeah.
I planted a seed, it's called the Nernst equation. Why don't I do that now? Then I'll do, this is, it. You know, most of you probably are wondering, well, how does, and we're getting to know how an antenna transmits power, but how does it receive power? It's a fair question, right? So here's how it receives power compared to the way it transmits. But first, let me go ahead and just do one other thing. I'm going to set up a circuit. I'm going to explain it from a circuit's perspective. In other words, if we really created a device, this is how, or created a voltage source with an antenna, and we had another antenna we wanted to receive the signal. I'm going to go through the whole 9 yards. This should answer questions you have, and also it will spawn some new ones that I can address as we're talking, okay? And if you want to open that back door to get a little more circulation, you can. It's up to you, though. All right, so first, let me show you a circuit, kind of a typical circuit. I'm simply going to put a voltage source, and I'll just call it V naught cosine of omega naught t plus a phase angle, volts. Now this is standard. Everybody recognizes this. All right? Really, we won't do it in the time domain. We'll just use V naught at some angle theta. That's the way you were taught to do it in circuits, right? That's a peak voltage value. Now I'm going to put some resistance here. That's a source resistance. And this is a typical type of thing you would see if you try to drive an antenna with a voltage source in your labs or something. This is what it actually is represented by, a voltage source with the source resistance. Now I'm going to put on the antenna. So far we can put on a short dipole or a small loop, or any combination. Now you don't need to know with the short or with the small loop's radiation resistance, but for kicks, no, I'm going to put a short dipole here. We'll do it that way. If I put a short dipole here of length L, right, then what I could say is this short dipole, I know if I'm at a given theta away, I can find very easily the average power, and I can find the electric field or the H field according to the equations. And what I'm going to do is this. Now, does everybody understand what I've got here? I've got a short dipole, and you can make the length arbitrary, but it's going to be a short dipole here. And what's the criteria for a dipole being short rather than not short or long? Anybody? Anybody at all? L has to be short, right? Short in what respect? It has to be a tenth of a wavelength. So a short dipole, the length of the antenna has to be less than or equal to lambda over 10. That's important. Remember this, okay? And out of curiosity, what is lambda if we're talking about free space? It's a wavelength, right? What's the general equations? It's proportional to the speed of light c, and it's inversely proportional to frequency, right? So in free space, we'll call it lambda naught is just c over f. Higher the frequency, the shorter the wavelength. That's the way to kind of keep this in mind. Now, at this point, I've got my short dipole. This is the circuit that I can use. I know I'll have a current I naught. And I can also say from a circuit perspective, what it looks like is this. I have a voltage source, V naught, at some angle theta. I have a resistance RS, and then I have what? R rad here, right? A radiation resistance. You all agree with this? So what I really need is this current. All right. Now, if you remember, R radiation for a short dipole was what? 80 pi squared length over lambda squared, right? That's an ohms. I would give you this equation. I'm just going through this. If I'm moving too fast, put up a hand. And I know some of the note takers, and I really appreciate it. You need to let me know. I need to slow down. Is everybody clear on this so far? See, you know all this. That's the reason I'm kind of zipping through it. But I'm getting at the point. Is it warm in here or is it me? Can you open it back door? I'm hoping for the best. Okay, now, we can obviously find, if I give you RS, I give you RRAD, you can find the current I naught simply by saying it's equal to V naught at an angle theta, you don't even need theta in general, over RS plus RRAD, right? Correct, class? Now that I've got the current, if I give you any values for RS and length, you can calculate the current if I give you V too, correct? We've got all that. What's my next step if I ultimately want, at some angle theta, at some range R, I want the average power density, the E field and H. What would be my next step? You all agree we got the current, right? Anybody?
Yeah.
Say it again, I'm sorry.
Radiated power.
Yeah, how do we get the radiated power?
1/2 RRAD times R naught squared.
1/2 times the radiation resistance, right? Times I naught magnitude squared. Make sure you put magnitude down there because you get a real and complex number. If you have a real plus J imaginary in your calculator, it's strict magnitude, got it? So now we have P rad. Give somebody else a chance. What's the next step? I'm looking for the average power density out here. Remember what I told you to do?
Yeah.
What do we do? Well, we assume there's no focusing, right? Just get the power density as if it was isotropic, right? And then add the focusing power. So we can say P ab at any point will be the power radiated, and that's what we got above, divided by 4 pi r squared. Now that's the average power density, correct? There's one more thing we do after that. We multiply it by either the gain or directivity, assume the efficiency is 1, right? And for any short dipole or small loop, the gain will always be 1.5 times the sine squared of the angle theta. Is everybody with me on this? Now we've done this several times. This is like the third lecture I've mentioned this, right? We can easily get, if we have the power density, which is in watts per meter squared, right? We can get the E field, right, from the formula, 1/2 magnitude of E squared over A to 9 is equal to the average power density. We can say the E field's magnitude is square root of 2 A to 9, right, times average power density. And just for fun, to be clear, this is a magnitude and it's the only thing we care about. How would I get the H field, anyone? Assume we're in free space. Magnitude of the H field at that point?
You divide by 8.
Right, everybody here? Divide by the, and what is the characteristic impedance of free space or air? I like to use eta naught as 120 pi ohms. Now you can put 377 if you want. I'd never take off points for that little being off a little bit, but 120 pi ohms is usually the way we write it, okay? That's also the characteristic frequency for the wall voltage, right, in omega. If it's at 60 hertz, omega would be 2 pi, or well, if you think about it, right, it'd be 120 pi hertz, which is kind of interesting. I think that's a coincidence, not by design. You all with me on this? Now, so anywhere we're at, we know how much power density there is. Here's how you calculate how much power is received and then how much voltage. This is called the Friis equation, so write this down. But it's a logical question. Friis equation. What the Friis equation does is this. It says if I have an antenna 1, all right, and antenna 1 has an incoming power P radiated, and antenna 1 has a gain G1 as a function of theta or phi, or theta and phi. Remember, gain is not a function of R, right? Correct, class? So we know this. Then if we're at any range, R, and we have an antenna here, a second antenna, and I'm going to get to some of the importance of this. And here you're going to have to say that it's going to be into a load that's mapped. Well, I'm going to leave it like that for now. This is a second antenna, right there. All right? Now, here's the key. You know how to go from here, if you have the gain, to get the power density, right? Now this antenna has some angle theta here. I'll call that theta transmitted, and this is theta received. And you can say the length of this antenna is LT, and call the length of this antenna LR for received, all right? I'm using short dipoles because we've been using them a lot. You're going to see how this is going to work. Everybody got the idea? I'm transmitting power. I want to see how much that second antenna receives. So logic says if you're receiving something and it's a power, you would want to know what the size of the object is that's catching it. Think of a catcher's net catching something. Right? Well, the electrical size of this is called the aperture. So write this down. For this antenna, right here, which is the receiving antenna, the size is called the aperture. Now in the book it's probably going to be either AP or AE. Either symbol is used. And the aperture is equal to lambda squared over 4 pi times the gain. Write that down. That's the electrical size, and the electrical size is in meters squared. So the gain of the antenna is proportional to the aperture, but you notice the size is dependent on lambda squared. You got that? Now, if you look at this, if we assume for a second both of these are short dipoles, I want you to just follow this. All right? Remember, the gain of a short dipole is what? 3/2 or 1.5, and that angle is 90 degrees, isn't it, class? Now listen to me carefully, right? When this angle is 90, it's 1.5. But if it's at any other angle, you have to take 1.5 times the sine squared of that angle. Does everybody hear me on that? And what's the gain, straight up or straight down? 0. Remember, no power is launched off the ends of that antenna. Okay, that's real important. So if we were to take a look at the P received here, now write this down. Power received. And what I'm showing you, by the way, is generally the way you would always do an antenna problem. If you have, you have microwave links, you're going to have systems that communicate from one tower to another tower with their cell phone. You're going to have things, if anybody hunts out here as a fisherman's out in the woods, you possibly can have some kind of not a walkie-talkie, but a transmitter receiver, and you'd like to know, especially if you're up in Alaska or something where you're maybe 50 miles apart or 25 miles apart and there's no cell service, and you don't own a satellite phone, then what you have to do is go through this kind of link equation and calculate what the power density is. And you want to make sure you get enough power density, and you want an antenna that has enough gain. Has anybody ever been out in a real remote area where there's nothing except walkie-talkies or something like that? All right, well, I have been on the aircraft carrier Eisenhower. It's loaded with all kinds of electromagnetic equipment and transmitters, receivers. However, if you want to talk to somebody, a buddy on shore or something like this, you can't, it's not a military. The only way you can do it is by fashioning something that's going to have enough power. You can do this kind of stuff. They don't get mad at you as long as it doesn't interfere. But believe me, it's not something that you can do unless you know what you're doing with this stuff. This is the beginnings of that, what I'm showing you. It's easy to do. So anyway, when you have this right here, if that's the effective area, follow me on this. I'm going to come down and I'm going to say, I know the average power density right there from that antenna, P average, we just did this, would be the gain of this antenna, and I'm calling it 1, G1, right, times the power radiated over 4 pi r squared. You all agree that that's the power density from the first antenna right here. Agreed, class? Okay? Now, what happens? If you want the power received, you multiply this by the effective aperture. I'm going to use AP here. Or multiply this by lambda squared over 4 pi times gain of the receiver, or I can just call, how about I call it gain 2, it's the receiver. Probably it would have been better if I called this G sub R and this G sub 1, but you understand, this is antenna 1, this is antenna 2, it's receiving. Y'all see this? Now here's the thing, the nice thing about this is the receiving pattern, how it receives power, is the same as how it transmits power. Okay? That's really beneficial. So now I'm gonna just do something here. I'm gonna say that both of these are short dipoles. Both short dipoles. And if they're short dipoles, you know one thing. You know what the radiation resistance is that I put right there, don't you? Correct? And you also know the gain for a short dipole. I didn't put this, but this one you have to know. And I'm going to put it right here. Maybe I did put it somewhere. Yeah, I did, but I'm going to put it here. The gain itself for a short dipole is 1.5 times the sine squared of the angle theta. And theta is always measured from the axis the antenna is on to the radius vector r. It's real important you get that. It's a sine squared. So what I can say is, this is the power received at antenna 2. Are you with me? You all with me on this so far? Now what they usually do to make it easy, they take the ratio of the received to the transmitted power, or radiated power. And I'm going to put that down over here. Now I understand it's going to rain like crazy, or rain a lot, later this afternoon through tonight, I guess maybe even tomorrow. I'm mentioning this only so if you don't have an umbrella, you're going to find one if you're going to be going around campus. So now if we take a look at this, this is the actual Friese equation. It says if you have two antennas, I'll call this transmitter and this receiver. You have a distance r between them. Then you can say the power received divided by the power transmitted or radiated. This ratio would be equal to lambda over 4 pi r squared. Let me explain that, where that came from. Times gain of the transmitter, and that's going to be a function of the angle of the transmitter, with the radius vector times gain of the receiver. And it'll be a function of the angle of the receiver. I got one more thing to tell you. Now how did I get that? Y'all see how you got 4 pi, right? I'll let you write it down. I feel for you people writing fast. I'm going to try slow. Y'all understand you would have 4 pi, right? This is the new part. That's the effective area or aperture. You can just put down area there. Then you have an r squared and you have a lambda. So lambda over 4 pi all squared would appear here. Y'all see this? Now, the gain of the transmitter depends on the antenna, right? If it's a short dipole, it's 1.5 times the sine squared of theta. If it's a small loop, it's still 1.5 times sine squared of theta, right? But there, the loop has to be perpendicular to the axis that the angle theta is measured from. And the thing that's really different between the small loop and the short dipole is the radiation resistance. Got that? There's I put up the radiation resistance for a short dipole for a loop. It's 320, right? Pi to the 4th, then it's going to be S over lambda squared. And that's kind of an awkward formula to remember. I would give that to you if I ever had a question about it, okay? So don't panic when it comes to some of these formulas. Now, you can find the power received here doing that, but here's some things that when you tell you have to consider. Please understand, this is the real world we're talking about. So, suppose I have, it's not going to work what I want. I have an antenna, you hold that. Now keep an eye, it's vertical. Hold it in the middle, All right. I've got them both aligned, and you see this one's going vertically upward, that one is, right? If they were both short dipoles and I wanted the total power received, I could get power transmitted over 4 pi r squared. That would be the distance. You all follow me? Then I'd multiply it by the gain. What gain? 1.5 times the sine squared of the angle measured from this axis to the radius vector. Got that? That'll give me the power density. How much is received of that power? I take the electrical size, lambda squared over 4 pi times the gain. What gain? Well, that gain would have to be the gain associated with this antenna. If it's a short dipole, it's 1.5, and it would be the sine squared of the angle that this antenna makes with the r vector. You all follow me? Now, here, I've got the r vector this way. What happens if I do this to the amount of power received? Just think about it. If I take the antenna from vertical and I do this, does the power go up or down? Well, y'all see that this thing is more perpendicular with R? The power goes up. You all see that? It's actually going to go up as the gain is the function of that, because the gain of this one, the angle between the axis of the antenna and the radius vector, would be 90 degrees. Do you all see that? And if I went like this, how much power would be received?
0.
You all got that. All right, now that's one aspect. Now, here's a second. Hold that up. Hold it up a little higher. Now, what if I do this? What does your gut feel tell you? Here's my receiving antenna. If they're aligned like this, that's maximum amount of power received, right? What happens if it does this?
0.
Well, your gut feel is nothing's going to be received because the E field is polarized in this direction. You all see that? And your gut feel is right. If I cock it by 90 degrees, it's nothing. But if it's by 45, it'll be off by the cosine difference of, you might say, the angle between this one, if I project it right onto the axis, and that one. You all see that, class? It's actually the sine of that angle. All right, cosine. Yeah, cosine of the angular difference. Now, I'm trying to get you to see physically in your mind's eye what's going on. This is maximum, right? Now, if I take this antenna or this one, I do this, I get 0 this way, right? Or if I take either of these and do this, I get 0. You all see that? That's called polarization loss. And what you have to do, and I'll give you more info on that, when you look at an antenna problem in general, you don't just take a look at the angular difference between R and this axis. You also want to see what the called tilt angle is on that antenna alignment. Are you with me? And it's going to fall off as the cosine of that angle. Now, I'll give you more on this in a second, but then what it means is these two equations, the gain of the transmitter and gain of the receiver, are assuming that the things are aligned vertically, or at least they have a vertical component. Then you have to take this and multiply it by the cosine, and you can call it the tilt angle tau. I'm going to give you more on that, and his book has more. And I'll give you problems and examples so you can really, understand it better. Does this make sense what I'm saying? And that's very important when you have antennas, because I have seen this personally. If you try to receive a signal, and you're in free space, say, and you got an antenna transmitting a vertically polarized E field, with an antenna this way straight line, you get zip, and you're scratching your head by the way this happens. Now, usually if you're in an environment like this, you'll get something, because the waves ricochet all over the place, and the reflections do have a component of polarization in the direction of the antenna. That's indoors. Your cell phone, you used to have just a little thin antenna, straight one. Anymore, I think I'm not certain about this, but I believe they're patch antennas in a lot of new phones. The iPhone has a patented antenna. I'm not even sure what it looks like. But they're antennas that are trying to be available to get information from all polarizations. It doesn't matter the polarization. And the other thing about your cell phone, if you think about it, it should be able to get a signal from that direction, straight up, straight down. Follow me? In general, what they do is if you hold the cell phone up like this, anything polarized in the vertical direction you'll catch like this. But if you take this and do this, now if you're close to the ground, there's a lot of reflections. You're going to find the signal strength's going to fall off. Because they have automatic gain in these phones and everything like this, you might not detect it with the voice, but all of a sudden packets will start dropping. Have you ever had packets drop where you're talking, there's like nothing, talking nothing? That's what's happening there, probably. So I'm going to tell you all this has a direct application to things you're familiar with, and there'll be more information on this forthcoming. So overall, this is the Friis transmission equation that I'll give you things about, information about. I wanted to put that out there now. Okay? I'm going to do the halfway dipole too, and I'm going to do arrays, but this is kind of fits very well right here because we've got simple antennas to talk about, okay? And I'll give you the problems with this. Now, I'm going to do the arbitrarily long dipole, and then the halfway dipole. Halfway is something, it's a go-to design. And I'll talk about the effect of the ground too. Now the math on this one is a little cumbersome. So I won't require you to do that. You can take a look in the book. Where is this arbitrarily long dipole? It's really a straight wire antenna. What page? Anybody tell me? I did this too because it helps get you ready for the quiz. That's the reason I showed this. So here's the arbitrarily long dipole. Do you have a page number on that, Jeff?
Is it after the first equation?
No, it's arbitrarily long.
Okay.
That's Friis you're looking at. That's a raise. That's a halfway. Let me turn the page.
Yeah, sure.
One more. Relax, you got time. One more. There we go. On page 449, it shows you. So this is going to be, again, a straight wire antenna, but now the length of this, L, is going to be greater than, or better yet, do it this way, it's going to be of the order of a wavelength. It could be a half wavelength, it could be 3/2 wavelength, but it's longer than a tenth of a wavelength. Got that? We're still in free space. When we talk about antennas, another thing, we always assume the voltage feeds them differentially right at the center. They don't have to be fed this way. But if you don't do it that way, you're going to have some behavior that's anomalous, and I don't want to get it there yet. It's center fed, symmetrically fed. Now, if you got an antenna that's fed like this, and you were to look at the current profile, call this I as a function of Z. Let's call this the Z-axis right here. And this will be the origin here. So the antenna is along the Z-axis. It's got a length L right here. And here's the kicker. Now write this down. Remember, that's the origin. That's Z equals 0. IZ itself will have a magnitude of I naught. But then it's going to be times the sine. And there's different ways to write this, but it'll be beta over 2, right there. And it will typically be Z, the height, minus, well, actually, I think the way it does it in the book, now that I think about it, they leave beta out in front. Sorry. I gotta actually make sure I write the way he has it in the book. Yeah, he's gonna have L over 2 minus Z. What he does is have the L over 2 first, minus Z. Let me talk about that for a second. So this is the current distribution. It'll be symmetric about here. And it'll go like this. It'll look something like this. And he has this drawing. So I'm trying to show you the magnitude of the current in this direction versus the plot. Now one thing you'll notice is it's not a maximum here necessarily. Y'all see that? It depends on this. Now I want to talk about that for a second. I know I'm going a little quick. I'm gonna let everybody catch up. That is on page 449, right?
448 is this equation.
448, I think.
8.67.
It starts about there. This is this is the equation. But what's important to see is what's going on here. So let's take a look at just the sine of beta. Well, beta is 2 pi over lambda, right? And then you have the length of the antenna over 2 minus z. So follow me on this. Let's take a look at the value of this sine function for different values of z. Are you with me? Y'all know I'm just taking that sine. I'm ignoring the I naught. I'm putting it up here. What happens when z is 0? Well, the sine is what? It's really pi L over lambda, right? So what if L was lambda over 2? Right? So I really have pi. I'm right at the origin. I'm where the feed point is for the voltage. You all understand? I'm right here at z equals 0, and I want to know what I would be. Well, if I look, and I'm evaluating this. I know I'm going to weight it by I naught. So if I have this, then I have pi L over lambda. So if I make L lambda over 2, I have pi times lambda over 2, don't I? So really the lambdas cancel, and that would be 1. Pi over 2, what's the sine of pi over 2?
0. Oh, pi over 2.
1, right? 90 degrees is 1, correct? So it would be a relative maximum. Now what happens? Go ahead.
Wouldn't the 2's cancel?
Well, they do, but what happens here? If L was lambda over 2, right? Then you get pi, lambda over 2 divided by lambda is pi over 2 sine of 90, right? Let me put up the actual equation. This is the actual equation. Beta I'm putting down as 2 pi over lambda. I'm letting z equal 0. And now I've got L over 2 here, minus 0 if it's at 0, correct? With me? Now, follow me. Remember, when it's L over 2, lambda over 2, it's called a half-wave dipole, and the current's a peak there, where the feed point is, right here. Which means you're going to get an impedance. You're going to have the voltage there divided by the current. You could replace this antenna with an impedance. But what happens if L is lambda? This is the point I think you were looking at. When it's lambda, what happens? Well, I have lambda over lambda, right? And then I have the sine of pi, which is, it's 0. The current goes to 0, right? The impedance, if I took V, any voltage divided by 0 is infinite, right? That would not be good either. I mean, that's not good. So you have to understand that what happens to the feed point impedance of longer antennas is they go from something that we're going to calculate in a second that's a relative min, all the way up to infinity and back down to a relative min. Follow me? They're not. If you just take an arbitrarily long antenna and feed it, you can't bet you're going to find much current in there because the impedance is so high. Are you with me on this, everyone? There's a lot I can talk about. I have just enough time to do these slides. So if we have an arbitrarily long antenna, and this is the current distribution, then the logical question is how would you calculate the electric fields from it? Y'all agree? And here's the way we always do it. I call it the building block approach. We find the electric field from a little chunk of current anywhere on that antenna. In the far field, all we got to do. And then we integrate that field value over the length of the antenna, and that's basically the total. This is the building block approach. So let me just tell you right now, if I have, and in his book he has this, if I say that I'm at a height z here, I think he uses z prime. I better write it over here. This is my antenna, it was length out, arbitrarily long. This is the origin, and this is vector r to my point of observation, P. And I'm out here, and I'm at a distance above here of z prime, I think he uses in the book. And I'm going to say I have a little chunk of current here. And this current is going to be some I of z dz in the az direction. And this is going to be R prime here. Now just understand something, this is not drawn to scale. I'm assuming I'm a long way up, and you could put down far field. Far field for the E field. Now, here's the thing, just listen. If you're a long ways away from this antenna, say you're 500, R is 500 L at least, maybe 5,000, then aren't these rays about parallel? You with me on that? And that's an assumption. So they're going to say the distance here, difference in the actual vector R and R prime, this distance here would be really, if you think about this, if this is angle theta, I'm probably not going to have time to do justice to this, but you're going to get enough of it. If this is angle theta, now just watch this. If that's angle theta from here down to here, then this is angle theta as well, if you look. Y'all agree with that? If you think about, you know, if you look at this small triangle right here, this angle, and, wait a second, I did that wrong. This angle here would be this angle here, my bad. I've got a messy drawing. Let me do this right. This I'll call R, and here's R prime. They're about parallel. And now I want this distance D, and this is the angle theta. And I know this distance D, if this is at a height Z prime, to be equal to Z prime here times the cosine of theta. And I'll explain why in a second. Y'all see, if we're taking a look at the difference in distance between this vector R prime and this vector R, if they're going out 90 degrees, there's no distance difference. Do y'all agree with that? If you would basically have two rays that are parallel, right? Well, if you think about this, Z prime doesn't matter because the cosine of 90 would be 0. But if you're going straight up and theta is 0, that's the maximum difference in distance between R prime and R. And it would be just this spacing would be Z. And the cosine of 0 would be 1. Okay? Just go with me on that. I'm not going to have time to finish this thing. I'll finish it with one other thing to give you. I'll go through and show you what the E fields are and what the radiation resistance is, and we'll finish this on Wednesday. So now I'm going to do this. I just want to get this to you. It's an easy. Fill up this